Let's talk normal distribution calculations. So last week we talked about normal density curves. We talked about the 68, 95, 99, 7 rule. So how to calculate percentages if we happen to fall at exactly one of the standard deviations. So for exactly one standard deviation above or below, exactly two standard deviations above or below, and three standard deviations. Okay, so those are our cutoffs. If you ever land exactly on one of those cutoffs, you can use that 68, 95, 99, 7 rule to approximate your percentages. The problem is, with real life data, you're not always going to fall perfectly on one of those spots. And so we need to talk about how to calculate those percentages based on the area under the curve. So when we don't land exactly on a standard deviation, how do we get our percentage that we want? So the standard normal distribution. So to start working with normal distribution calculations, the first thing we need to discuss is the standard normal distribution. Now this is a normal curve, but it's a special type of normal curve. This is a normal curve that has been standardized. We have calculated the z-scores, and we are looking at the distribution of z-scores for our data set. So last week, when we looked at normal distributions, okay, we had an example where we were working with pregnancy lengths. So the mean pregnancy length was 266. The standard deviation was 16. So 16 days magnified with one standard deviation above, that would be a pregnancy that lasted 282 days, 298, and then 314. And then we did the same thing on the other side, just subtracting. So one standard deviation below the mean would be 250 days, and so on, right? And so once we had this normal distribution drawn, we were able to mark off our boundary points, find whatever percentages we needed using that 68, 95, 99, 7 rule. Now the problem with this, if we use this normal distribution, this only works for pregnancy lengths. Right? So if I was looking at area under this curve, I can only do it if I know where the pregnancy length ends, and then I have to calculate area underneath the curve, which isn't going to be very useful because most of us don't have the calculus knowledge to do something like that. We don't know the equation of this curve to integrate and calculate area. Okay? So what needed to happen was we need to take our normal distributions, and when we standardize, so when I take those pregnancy lengths and I standardize each of them, I stay or maintain a normal distribution, but now I've rescaled and I have shifted it using that z-score formula, x minus mean divided by standard deviation. Every time I standardize a set of data, I am forcing it onto what's called the standard normal distribution. So it's going to be a normal distribution. It's going to be measured only in z-scores. So our values aren't going to be in days or inches or pounds or whatever we were measuring in our data. It's only in z-scores. So we have a z-score of 1.7. That means that's 1.7 standard deviations above the mean. If I get a z-score of negative 2.5, that means I'm 2.5 standard deviations below the mean. So we're going to know our location within the distribution based on that z-score. The other thing, every standard normal distribution has the exact same mean and the exact same standard deviation. When you calculate the z-scores for your distribution, you are shifting the data so that the mean becomes 0, and you're also rescaling the data to make the standard deviation of the distribution 1. So every standard normal distribution is going to have these two arguments. The mean is at 0, the standard deviation is in 1 unit length. Okay? So here's what that looks like. Every standard normal distribution is going to have this exact same look. So exact same curve, exact same labeling on the x-axis. 0 is our mean. It's going to be right in the middle. And then our standard deviation happens at 1 unit at a time. So 1 standard deviation above the mean, 2 standard deviations above the mean, and so on. So with these types of questions, when we start doing the calculations, which we'll get to here in a second, the first thing I would always do, because you're going to have to draw your normal distribution. So you're going to have to draw a sketch. What is this going to look like as far as area under the curve and things like that? So draw your normal distribution and label your x-axis. It's going to be the same every time. 0 for the mean. 1 standard deviation above or below happens about midway down the hill. 2 standard deviations above or below the mean is going to happen kind of towards the bottom of the hill. And then 3 standard deviations is always going to be kind of right out in the tails there. So label your x-axis every time. Just make little tick marks at 0, 1, 2, and 3 above, and 1, 2, and 3 below. It's going to make it a lot easier to determine where you want to make your cutoff when you draw your picture and shade your area. Okay, so standard normal distribution, mean's always 0, standard deviation's 1. This happens every time we take a set of data and standardize the values. Okay, so today, what we're going to discuss, there's 2 different types of calculations that occur with normal distributions. Today, we're going to talk about finding area under the curve. So given a situation with a standard normal distribution, what's the area, what percentage of observations are going to fall within a certain range of values? Tomorrow, we'll do about the same thing, and tomorrow's we'll actually start with the area under the curve, and we'll work our way back to a specific value. So there's a forward calculation and a backwards calculation. We're going to do forward today. So an area under a density curve, when we're talking about finding area under the curve, we are going to be calculating a percentage or a proportion of the observations in that distribution. So when we draw our normal curve, one of the things we're going to be doing is standardizing our value. So we're going to be getting how many standard deviations above or below the mean we are. We're going to be looking at a specific range. What percent of values lie between negative 1.6 and 2.1? What percent of values lie greater than 1 standard deviation? Things like that. So when we talk about what percent of observations fall within a certain range of values, we're talking area under the curve. And that's where that table that I handed out to you guys comes into play. If we had to calculate area by hand, we would have to learn, like I said, the calculus behind it first, to worry about how to find that area and things like that. They've already taken care of that for you. So that table that I passed out, and we're going to learn how to read here in a second, tells you every area you need for these problems. So all you need to do is look up the z-score that you are associating with your value and report the area under the curve. Okay? So, the table. It's called either Table Z or Table A. Your book calls it Table A. If you were to look it up online, usually if you type in Table Z, you're going to have the best results as far as finding this specific table. Okay? So Table A gives you the areas to the left of your specific z-score. That is important. You want to write that down. When you look at Table Z or Table A, it will give you a list of areas only to the left of the z-score. So when you calculate a z-score and you look it up on Table A, it's only going to tell you what percent of observations lie to the left of it. Some of the questions we're going to be concerned with are going to want area to the right. Or we might have 2 z-scores and we want to know the area in between. So when you look at the table, we're going to have to do some manipulating with our values because the table can only tell us to the left of our specific z-score. Okay, so it's very important that you recognize on the table you're only going to get areas to the left of the specified score. So let's talk about how to read the table here. So when you're looking at your table, the columns, if you look at the left-hand column of your table, now if you look at front and back, the only difference between the 2 sides, one has positive z-scores, one has negative z-scores. So once you've calculated your z-score, or you know what z-score you're trying to look up, you have to make sure you're on the right side. So am I on the positive side or am I on the negative side? So the left column is going to give you the start of the z-scores. Every z-score, and this is something else you probably want to write down. When you calculate z-scores, you're going to keep 2 decimal places every time. Always round to 2 decimal places. So the left column will give you up to 1 of the decimal places. So if I have the value 2.76, my first step would be to come to the column and find 2.7. I need to find that first decimal place with the units. Okay, so 2.7. Then if I wanted 2.76, I need the hundredths place. That hundredths place is listed across the top row. So along that top row where you see 0.00, 0.01, 0.02, that's the hundredths place of your z-score. So you're going to use the column to find the start of it, the row at the top to find the hundredths place, and then basically you're going to find where they meet up. So you're just going to follow across and down. Wherever they meet up, that's going to be your value that you're interested in. So the values inside the table, those are your areas. Those are your percentages. When it says what percent of observations lie left of this particular value, or what percent of observations lie between these two values, those are going to be your areas. So you want the values given to you in the middle of the table there. Okay? So the left column and the top row deal with your z-score, which you're going to have to calculate to start with. Once you know where your z-score is located, you follow it to where it overlaps, and that's going to give you your specific area. Now again, the area that's reported in the table is only to the left of that particular z-score. So depending on what the situation calls for, you may have to do some work with the area that you find. Subtracting from 1 or subtracting the two values, whatever it may be, and we'll talk about that here in a second. Does everyone feel okay, at least in terms of reading the table? And we'll talk about the areas, meaning how we use them here in a second. But do you understand? Make sure you're on the positive or negative side. Column for the first digit.
For the top part, are they gonna like tell you what place to go to? Or, like,
Your z-score will tell. So like if I was going to say, like my z-score is negative 1.75. Okay, so I've rounded to two decimal places. I'm going to find the negative 1.7 here. And then I'm going to find, since I want 5 for my hundredths place, I'm going to find the 5 here. And then I'm going to follow them to where they meet. Okay? So basically that top row, you want to look at what your hundredths place is and find that value. And then you're going to bring them together and meet. Okay? All right, so let's just do a couple real simple reading the table, getting some areas here. So find the proportion of observations from the standard normal distribution that are less than 1.4. And when they give you that value, that's 1.4 standard deviations above or below here. Is that 1.4 standard deviations above the mean or below the mean? Above. How do we know it's above the mean? Because it's a positive z-score. So since it's a positive z-score, it means our value is above the mean. Now, we want the percent of observations. We want the area less than 1.4 standard deviations above the mean. So if I want less than, then that's the area left of 1.4, right? So that's going to be exactly what we find on our table. So on your table, make sure you're on the positive side. I want everyone going through this process right now. So on the positive side, find your 1.4 on the left column. Since there's not a hundredths place, what value are we going to be using there? 0. So if they don't report a second or a decimal, we're going to assume it's 0. So we're looking for 1.4, 0. So then we look in the top row at our 0 and make sure we follow it down. So where the 1.4 and the 0 come down and meet, we get a proportion of what? What's the 4-digit number? 0.9192, right? So when I went to 1.4 and went to 0 and followed together, 0.9192. So that is our area left of 1.4, which is exactly what we wanted. So when you do these types of problems, here are two things that you need to make sure you understand. When you find your actual value, okay, reporting 0.9192 is not your answer. This is not a time where you can just say x equals this and be done. Requires an explanation. So this 0.9192 means that about 92% of all observations are less than 1.4 standard deviations above the mean. So this percentage means that's the area to the left of this 1.4 standard deviations above the mean. Okay? The other thing that you're going to have with your answer is a sketch of the problem. So you have to sketch your normal distribution. I would label the axis still. So 0 in the middle, 1 about halfway down on each side, 2 about halfway or down at the bottom of the hill, and then 3 kind of out in the tail. So 1.4, we'd go to our 1, go about halfway between 1 and 2, and make a line. That's our cutoff point. Since we wanted the area left of that particular point, we shade to the left. So when you draw your pictures, this is what it's going to need to look like. You need to identify the correct boundary mark. So where does your line need to be? And then you have to shade the correct area. Do we want left or right? Or if I have two values, do I want in between? Everyone okay with that idea? Okay. So let's try this one out. Find the proportion of observations from the standard normal distribution that are greater than negative 2.15. So there's a negative there. So the first thing we need to do is take our table. We need to be on the negative side. So go through and find the value associated with negative 2.15. So find the negative 2.1 on the left. Find the 0.05 along the top. Follow them until they come together. If you do that correctly, you should find 0.0158. Does everyone get that? Okay, so 0.0158 is our value for negative 2.15. Now take a close look at the problem here. We want the percent of observations greater than negative 2.15. What does the table tell us? What's the only area it can give us? To the left. It can only give us values less than a certain value, right? So when we see we have 0.0158, that means there's 1.5% of observations less than negative 2 or 2.15. So how would I get the probability or the percentage that I actually want, which is greater than? Subtract from 1. There's where that main idea of density curves comes into play. The area underneath is always 1. So if I know how much area is to the left of a certain value, if I subtract from 1, that'll give me the area to the right of that value. So if I take 1 minus 0.0158, that will give me the area I want, which is to the right of my actual value. So again, as far as a picture is concerned, you would go to negative 2, go a little past negative 2, make your boundary. We wanted the area to the right, so we would shade everything to the right. So if we take 1 minus 0.0158, anybody do that on the calculator real quick? 0.98 what? 42. So 0.9842, what does this mean? How would I interpret that as far as the context of the problem? Okay, so about 98% of our observations, about 98.4% of our observations lie above 2.1 standard deviations below the mean. So when you report your answers for these, you have to have that statement. What is that decimal that you've calculated? What does that value mean? Okay, and then you also need to make sure you have the picture to show that the shading helps you figure out whether you have the correct value or not. If you drew this picture of negative 2.15 shaded to the right, and you look up on the table and you find 0.0158, would 1.5% make sense if this is how much area I'm supposed to be covering? No. So you would know you have to do something with that 0.0158. So you got to do something with it to get the area that matches what your picture says. Okay? All right, so normal distribution calculations. As far as steps go, okay, the steps are going to kind of remain the same every single time you do a normal distribution calculation. So this is when we're working forward. So they're going to give us a value. So for instance, they might say you have the normal distribution, the pregnancy example. The mean number of days that a pregnancy lasts is 266 days, standard deviation of 16 days. What percent of pregnancies last less than 296 days? Okay, so what we need to figure out is, well, 296 days, how many standard deviations above the mean are? So what z-score is associated with that specific value? So once you know what the problem is stating, we want to standardize. Take whatever specific value they gave us and standardize it. Meaning what? When I say standardize a value, what's the process? We got to calculate the z-score. And how do we calculate z-scores? X minus mean divided by standard deviation, right? So you need to take the mean and standard deviation reported to you, take your value and standardize it. So value minus mean divided by standard deviation. This is going to be the first thing you do once you know what the problem's asking. Okay? So we have to calculate a z-score. Table A only works with z-scores, nothing else. Once we know what our z-score is, we can draw our distribution. We can get a sketch so we know about what we should be looking for. So once we know what our z-score is, we draw our normal curve. And depending on what our z-score is, we mark our z-score wherever it's supposed to lie on our curve. And then we determine, are we going less than or greater than? Do we want to shade left or right? So if it's something to the right, then we would just shade. And now we have our distribution. So then all I need to do is use table A, find the proportion or the percentage that matches my picture now. So my last step would be use table A, look at the z-score, and calculate the correct percentage. Okay? So let's do an example here. So the level of cholesterol in the blood is important because high cholesterol levels may increase the risk of heart disease. The distribution of blood cholesterol levels in a large population of people of the same age and sex is roughly normal. The mean is 170 milligrams of cholesterol per deciliter of blood, and the standard deviation is 30 milligrams per deciliter. Levels above 240 milligrams per deciliter may require medical attention. Okay? So, from the problem, things that we should be looking for or highlighting or whatever. First, it told us this is a roughly normal distribution. So we know we can use our normal distribution calculations with it. The next thing, with this normal distribution, it gave us the mean of 170 and it gave us the standard deviation of 30. Those two things are always extremely important to find. Those are our two values. 170 for the mean, 30 for standard deviation. Okay? So, the first question we want to answer regarding this distribution, what percent of people have more than 240 milligrams per deciliter of cholesterol in their blood? So if we have a normal distribution that has a mean at 170 and a standard deviation of 30, what percent of people have what's considered a dangerous level of cholesterol? Okay? So the first thing is figure out, well, exactly what are we asking us to do here? So let X, our unknown value, be the level of cholesterol in the blood. We know we have a mean of 170. We know we have a standard deviation of 30. Now, as far as X is concerned, we know the cutoff for it is 240. And if it's a dangerous level, that means that X has to be greater than 240. So the question's asking, what percent of people have a cholesterol greater than 240? Here's what we're looking at. Okay? So the first thing I would need to do is take this boundary value, this 240, that's our point in question, and do what with it? What do I have to do with that 240? Standardize it. 240 doesn't mean anything on the standard normal distribution. There is no 240, right? It goes from 0 up to a little bit above 3 or below 3. So 240 means nothing for that standard normal distribution. So our first step after that is to standardize. So we need the z-score for 240 milligrams per deciliter. So take the value 240 minus our mean 170, divide by 30. So grab your calculators and do that. I want to make sure we're good all the way through this whole process. $240 minus 170, and then take that divided by 30. And what do we get for a z-score? 2.33. Okay, so we're going to round to 2 decimal places. So 2.33. So here's what we're looking at. Our z-score, our boundary, is at 2.33 standard deviations above the mean. We want to know what percent of observations are greater than that. What percent of our observations are higher than 2.33 standard deviations above the mean? So once I know what my z-score is, I can sketch my distribution. Now, as far as sketching goes, I draw my curve. I would always label the x-axis, so your 1, 2, and 3 on either side are marked out correctly. And then we know our boundary is 2.33, so we go a little bit above positive 2 out here, make our mark, and since we're concerned with people greater than that, we're going to shade to the right. Okay, so we know our answer should be fairly small. There should be a very small percentage of people that fall within or into this category. Okay, so once we sketch, now we can use our table. So on your tables, look up 2.33. So make sure you're on the positive side. Always make sure that's the first thing you do is on the positive or negative side, depending on your z-score. So find 2.33. Tell me the percentage you find. $99. So what are the 4 digits? 0.9901. So when you do this, I do want you to report the 4 digits. So make sure you give me the decimal. So the proportion of observations less than 2.33, because that's what the table gives us, is 0.9901. We said, though, that we want the percentage greater than. So we're going to take that 0.9901 and subtract from 1. So if I take 1 minus the 0.9901, we get 0.0099, which now we have to translate into context. So that 0.0099 means about 1% of boys have a cholesterol above 240 milligrams per deciliter. So about 1% of all boys have a dangerous level of cholesterol.
So if this is like, since it's symmetric,
Mm-hmm.
if you're trying to go for like the right side,
Mhm.
then you just go to the negative side since it's the same thing.
Okay, that's a great question. So if you were noticing, the normal distribution is perfectly symmetric, right? So do something for me. Flip over to the negative side and find negative 2.33. Look up negative 2.33 on the table there. And what decimal do you get? 0.0099. So what Grace is pointing out here, if I were to look at it as a to the right type of problem, I have to look my value up, subtract from 1 to get the actual value I want. What she's saying is, well, couldn't we look at this also as maybe looking at, okay, if I were a negative 2.33 and look at the left value, these two tails should be exactly the same, right? So if I don't want to have to worry about subtracting from 1 at the end, she's saying instead of looking for that right tail, look for the left one. So instead of positive 2.33, look up negative 2.33. That's going to tell you the exact value you want. So yes, you could do that. So if that's a process that works for you, go ahead and do that. If you know you can just switch the sign on the z-score, and then it'll tell you the area to the left, and you know that's the same as the area to the right, you can do that. Okay? Otherwise, you just have to remember that when you look up your z-scores to the right, you have to subtract from 1 when you look up that exact value. Okay? Any questions on that? All right, let's do one that we haven't talked about yet. So far all we talked about is how to find something less than or something greater than. But there are times where we want to know between two values. So here we're asking what percent of people have blood cholesterol between 170 and 240 milligrams per deciliter. So first thing, if we think about what the problem is stating or what we're looking for, we want to know what percent of observations, what percent of X's are between 170 and 240. So now we're between two values. Okay? So once I know what my X values are associating with, so X has to be between 170 and 240, what do I need to do with my 170 and my 240? We have to standardize. We're in terms of X right now. We need to be in terms of Z. Z-scores are the only way we can work with our table. So we're going to standardize both of these values. Now, without using calculators, what's our Z-score for 170 going to be? 0, because 170 is our mean, right? If we land at the mean, we're not above or below our mean, so we're right at 0. 240, what's our z-score going to be? 2.33, we just calculated that, right? So if it's something that you calculated in a previous problem, you don't need to do all the work for it, okay? So we know we're going to get 0 for our lower bound, and we're going to get 2.33 for our upper bound. So we're going to want values, we want to know what percent of our values fall between those two z-scores. Okay? So as far as the sketch is concerned, on our normal distribution, we're going to make a boundary line at 0, right in the middle, and we're going to make a boundary line at 2.33. We want everything in between, so we want to shade everything between those two. Okay? Since we know what our two boundary points are, what do I need to do at this point? Use the table. So what are we going to look up on the table? What two values do we need to find on the table? 0 and 2.33, right? So we'd have to look up 0 and we'd have to look up 2.33. We have to find both values. Okay? Now if you think about it, what should 0 be? 50%. If I'm right in the middle of my distribution, I'm going to get 50%. So if you look at it on the table, 0.00 or 0.00 is going to give you 50% exactly, right? Now 2.33, we also just looked up, that was 0.9901, right? So what needs to happen here? When we want the area between two cutoff points, the table is going to report 99% of the data is left of 2.33. 50% is left of 0. We only want the portion left of 2.33, but right of 0. We want everything in between there. So when you are looking for an area between two values, you're going to take the right area, 0.9901 in this case, minus the left area. So always take the right value minus the left value. So once you have your two percentages from the table, take right minus left are always going to be big minus small, and that's going to give you your overall percentage. So for this particular problem, 0.4901 would be the percentage from our table. So in context, what does this 0.4901 mean? So about 49% of all boys are between the 170 milligrams per deciliter and the 240 milligrams per deciliter, right? So when you go to interpret, when you give that statement at the end, always go back to the original context. Okay, don't report between 0 and 2.33. We don't want the z-scores now. We want to know what that means for values. So about 49% of the values fall between 170 milligrams per deciliter and 240 milligrams per deciliter. Okay? So always make sure you have that interpretation at the end. If you just give me the 4 decimal answer, you will not get full credit for a problem. I have to have the statement. What does that mean in percentage, and how does it relate back to the context? And then also, do not forget to draw your distribution. Show me that you know where your cutoffs are in terms of z-scores and what area you happen to be looking for. Okay, so all those things have to be included. Okay there? And that's it. That's all I want you guys working on today. Okay, so in the homework here, you only have 4 problems. Number 48, all it's going to do is give you z-scores and have you look it up on the table. So if z is less than, z is greater than, or z is in between two values, it just wants you to know how to work with calculating the correct percentages. Now 53 and 54, you are only doing parts A and B. If you try to do part C, you're not going to know how to do that yet. That's a backwards calculation. That's starting with a percentage and working back to a value. So parts A and B are the ones you're going to use first. And then 56, same type of deal, just finding percentages based on your normal distribution here. Okay.